Okay, so here we're going to be looking today at the product moment correlation coefficient. This is a measure of the correlation or the linear association between two different variables. We often shorten this to PMCC, the product moment correlation coefficient, often shortened to PMCC, and the actual notation for this is R. So we use the value R to denote that we're talking about the PMCC, the product moment correlation coefficient, the measure of the strength of the correlation between two different variables. Okay, so this is the formula as it's going to be presented to you in many textbooks and in the formula book. We're more interested in these two forms. So R is going to be the S of xy over the square root of S of xx, S of yy. All of these you should recognize the formulas for over here on the right hand side. You've been using them while calculating and working with regression. This middle form we would usually avoid. It's not the most intuitive, but it is the form that we used as the basis of how we calculate the variance back in straight maths. But these two highlighted forms, and actually the one on the left more so than the one on the right. So we should be able to calculate that correlation coefficient. You already know how to find the S of xy, S of xx, and S of yy, so I should be able to leave you there. But I'll quickly pick on some points. Okay, so the correlation coefficient always produces a value in between 1 and -1. So these numerical measures will be more accurate and more easily compared than our qualitative descriptors of correlation. Previously, we would say that two variables had strong positive correlation or very weak negative correlation. But these descriptors, as good as they are actually quite vague. How would I compare two different data sets that both had very strong positive correlation? If we have a numerical measure, we can then actually make a comparison between them, even if one of them is only slightly stronger than the other. We now have a quantitative numerical measure of the strength of the correlation. The correlation coefficient should always be in between 1 and -1. So that's your first sense check. And the closer it is to 1, the stronger that positive correlation is. If it is exactly 1, this is perfect positive correlation. All of the points on the scatter graph would be exactly on a straight line. Okay, so here's a few different scatter graphs and sets of bivariate data. Have a quick think about which ones would have the correlation coefficient shown on the right. So I have R equals 0.8, so that's strong positive correlation. R equals 0, no correlation at all. R equals negative 0.4, weak negative correlation. And R equals 0.96, extremely strong positive correlation. Which of these scatter graphs match up with each of these correlation coefficients? Where's the strongest? Where's the positive correlation? Where's the negative correlation? Where's no correlation? And here's how they should line up. So top left is positive correlation and it's quite strong. That's the 0.8. We have no correlation, bottom right. There didn't seem to be any trend in any direction whatsoever. Negative correlation was up here and it was quite weak. And I hope you spotted this extremely strong correlation in the bottom left. Okay, so just a couple of points I want to highlight for you. Firstly, because the PMCC is measuring the strength of linear relationship, outliers are actually going to have a massive effect. They can distort the PMCC. Now, you've looked at residuals from the regression line, and large residuals are going to affect the PMCC. If it's far away from that straight line, even though most of the others lie on the line, that one point will actually reduce the strength of the correlation quite significantly. Secondly, the word linear is also important. The PMCC is a measure of linear correlation. Just because the PMCC value is low or it doesn't show strong correlation, it doesn't mean there isn't a different type of correlation. So we didn't see strong linear correlation, but there might be strong exponential correlation. It might be a curve that fits this model or this data better. Okay, just be on the lookout and be aware of those two factors. Okay, so let's try out a question. Here we're told that the number of vehicles, X million, and the number of accidents, Y thousand, in 15 different countries were recorded. Here's the scatter graph. The following summary statistics were calculated. Okay, so we've got our summary data. From here, we should be able to find S of XX, S of YY, S of XY, and then calculate R from there. Part A of the question asks us to do exactly that, to find the PMCC, the product moment correlation coefficient. This is R, to find the value for R. And then, making reference to our answer to part A and the scatter graph, comment on the suitability of a linear regression model for these data. Okay, so right from now, I'm looking at the scatter graph, and these do seem to form a straight line. If the correlation coefficient shows that there is strong correlation, that means that a straight line, the regression line, is actually going to be a good model for the data. It's going to be a good model for predicting what might happen within this data set, or the larger data set, since this is just a sample. So if we have strong correlation between X and Y, we can recommend the use of a linear regression model for this data. Okay, let's get started. We can find our summary statistics. We'll start with the S of XX, which is the sum of the squares of X. And we have enough information to go into that formula. S of XX is the sum of X squared, subtract the sum of X squared over N. Okay, so these values were given to us. We'll just substitute them in. That's 2,576.47, subtract 176.9 squared, over 15. Okay, so we get a value for that. We'll do exactly the same thing for the S of YY. So the sum of Y squared, subtract the sum of Y squared over N, substitute those values in, just punch those into our calculator. We get 9,034.933. Finally, for the sum of the products, so that's S of XY. And the formula here is the sum of XY minus the sum of X times the sum of Y all over N. Substitute those values in, and we get the third value that we need to calculate the correlation coefficient. 1,907.627. Okay, the formula for R, using these three, the formula for R, the PMCC, is S of XY over the square root of S of XX, S of YY. So that's 1,907.627 in the numerator, and our denominator is going to be the square root of 490.229 times 9,034.933. Okay, so just some sensible things. I know that this is going to be a positive result. Looking at the diagram, we also had positive gradient. So substitute those in, and we get our R value. How strong is the correlation? 0.9064. So this is quite strong. This is very strong positive correlation for this data set. Okay, so that is the PMCC from the values we've been given. So as I said before, we do actually have very strong correlation. And because we do, we should be confident to use a linear regression model to work with this data, to make predictions and to interpolate. Extrapolation, however, is still discouraged. Okay, so you should be able to calculate the necessary statistics to find the PMCC.